Alright, so in this video, I'm going to be explaining another important article with the title Domain Generalization via Adversarially Learned Novel Domains. This paper in 2022. This study focuses on the domain generalization task, which aims to learn a model that generalizes to unseen domain by using multiple training domains. More specifically, we follow the idea of adversarial data augmentation, which aims to synthesize and augment training data with hard domains to improve the model's domain generalization ability. However, previous studies augmented training data only with samples similar to the training data, resulting in limited generalization ability. To alleviate this issue, we propose a novel adversarial data augmentation method, which employs an image-to-image translation model. It's similar to the idea of previous video, so it was like cycle GAN, similar to that idea. So to obtain a distribution of novel domains that are semantically different from the training domains and at the same time hard to classify. So we have K domains, and then we propose an image-to-image translation model to convert source domains into novel domains. The proposed model is built on DLOW, so we introduce DLOW in this section. DLOW is trained on multiple domains and takes one of the training domains as the source domain. It can transfer an image from the source domain into an image with an intermediate style among all training domains. And the proposed DLOW considers a domain code space that encodes a mixture of multiple training domains. The domain code Z controls the style of the generated images. So this reminds me conditional GANs, where we have some variable to control. So assume that we have K training domains, T1, Tk. So Z is defined as K-dimensional vector, where some of them is just 1. And each element represents the degree of relevance to the target domain T sub K. By specifying Z as generation time, DLOW can convert an image in the source domain into an image with a style specified by Z. The objective function contains the adversarial loss and cycle consistency, and DLOW results in two maps. G sub ST, which learns a mapping from source domain to target domains, and GT sub S. So G sub ST goes this direction, GTS goes T, so it's like an idempotent. It's like identity. If you do it twice, once, and then second time, it comes to itself. So image to image. It's like autoencoder, image to image. So we only utilize this cycle consistency loss that we discussed in the previous video. So you see the similarity. We only utilize G sub ST in our proposal. So we take G sub ST as an example to explain DLOW. For K target domain, DLOW models introduces K discriminators that distinguish generated images and images from domain T1, T2, T sub K, respectively. The discriminator D sub S for source domain distinguishes generated images and images from the source domain. Then for each K, the adversarial loss between S and T sub K is just, see this, the standard adversarial. You have discriminator, and then we have generator, so very classic. This is an overview that we first just sample from normal distribution to control what we want. And once we have an image, we can translate it to another image. And there is a cross-entropy loss for our classification. So this is the full adversarial, and this is the cycle consistency loss, because it's like reconstruction loss. So once we have this cycle loss and then adversarial, this is the total loss. And we first propose a conditional generative model with better cycle to synthesize augmented samples. So they use it for just synthetic images. And then we propose utilizing the distribution of domain codes to represent data generating distribution of the D-log-B model. Finally, we propose this min-max optimization to enforce the generative model to synthesize hard examples by finding the worst-case distribution of domain codes. So this author proposed a weak version of cycle consistency. Instead of forcing generated images can become recovered, they enforce that features extracted by the discriminator can be recovered. Inspired by a weak version of cycle consistency loss, we replace the cycle consistency loss of the original D-log model with a weak cycle consistency loss. We call this new model D-log-B. So D-log-B is a weak version of D-log. And it is just this. FD sub S, this one is a feature extractor of source domain discriminator, and gamma controls is just balances the pixel level cycle consistency and feature level cycle consistency loss. Now you can see the original D-log model and the weak version of that we call D-log-B. You can see it visually, the effect of that. They tried it on MNIST and Street View, but this is just for MNIST. But it's interesting to see what happens on Street View as well. So if we have M Gaussian noise, then this is another way to control the images. And this packed dataset, we always use it for generalization. P stands for photo, A stands for art, C stands for, S stands for sketch, and C stands for cartoon.